My name is Sofia Cedres Cerqueda, and my team is Estefania Catherine Niño, and today we're going to present our third partial project, or last partial project, that is Solid of Revolution with avocado. So let's. Before to start to explain the project, we're going to explain what is a solid of revolution. That is also known as a volume of revolution. It's a solid figure obtained from rotating a curve around a straight line. The line used as a reference from the rotation of the curve is known as the axis of revolution. This information is important because we're going to use, in this case, the avocado, we're going to use the x-axis. So this is very important. A solid of revolution needs to be visualized in the three-dimensional space, as it requires having volume. Start with function f of x over an interval a to b. All this information was found in Studio Smart that it helps us to find any information about any root of mass. So for step one, first we have to measure the volume using word displacement. In this case, we use container with a capacity of 700 milliliters, but we only use 400 milliliters. So this is the quantity before to put the avocado inside. So we put the avocado inside and the measure or the quantity. After that, we have to find the difference between before and after in order to get the exact volume that the avocado has to have. That is here. Then the second part of step one is cut the avocado in halves and place it on a millimetric paper to get the coordinates. Sorry. As you can see, here are the coordinates. So it is very important. Then we start with step two, and we start to use technology that in this case is GeoGebra Classic. We place the coordinates in GeoGebra. This is the tool that we're going to use in all the project. We only put the coordinates, the specific coordinates as a point. We don't have to get a union between anything, just put the coordinates. This is step two. Then we start with step three, that is obtain the polynomial functions. For that, we have to use the command fitpoly and the coordinates for the avocado curve profile. As we can see, here we have the first function or the first fitpoly command, and this is the result. But as you can see, as it is divided with a segment from U to C, it also continues the line. We have the line that it's continuous, that is a graph, but we just need the specific segment that we are marking right here. So in order to find that specific segment, we have to rewrite the function that we have here. The reason is because here are decimals, and the decimals, they are not very exactly with the results. So we have to rewrite to fractions. And for this, we're going to use a GeoGebra CAS module that it's only rewrite. This helps us to rewrite the functions from decimals to fraction. This is only that the module helps us. And then we have the second part of step three, that is with the function in fractions, we have to use the if command. This is the first function. This is how to be seen after all the steps, but this is the exact way to write it. So we put the same command, as you can see, and then we use if. And between parentheses, before we have to write the specific points or the specific coordinates that we want to use. That is the specific segment also. And then we write the function. But the function, as I already said, it has to be written with fractions, not with decimals, only with fractions in order to get more specific results. And this is how it has to look before do the if command in each function. So we have the seven function, we have seven segments that also are divided with colors, that it's not very clear, but yeah. We are divided between colors. And then we start with step 4.
In the step 4, we use the algebra to simplify the function of the step 3 because in this step the function were squared, but we needed them in the simplest expression for the rest of the step. And for this, use the command that span in algebra and wrote the result of this command in the notebook. Continues with the step 5, um, where we solved each integral behind. I can see in these slides. According to the range of the corresponding section, after having evaluated them, you need to verify that they were correct, and for this, we use the algebra calculator. After this, we already had the value of each of the functions that we could later use to calculate the error percentage in the last step. In the step 6, we make the model in 3D, for which we use this command, that is the surface function, to evaluate 360 degrees in its axis. In algebra, because this to rotate each of the function on the x-axis, I can see in this image, and 360 degrees that is indicated in the command, and this way to obtain the 3D model, that is this. Each color to represent a function. This is a one function, second function, and the rest. Because as we work it in segment to reduce the number of functions to be integrated. Finally, in the step 7, the percentage, to calculate the percentage of error, in which we had to obtain the first, we need to calculate the total volume, and with this formula, and to substituting the data with the result of the integral in the step 5. And for the last, use this formula and substituting with this result, that is the percentage of error equal to 227.78 minus 200 divided by 200, and the resulting is the percentage of the error, that in this case is the 13.78 percentage.